For some time, I've been thinking about the following question. Where is the seat of EMF in a toroidal inductor? This was prompted after viewing a YouTube video of the same title, posted by Mr. Bob DuHamel, who regularly contributes under the headline banner, Vocademy, Electrics Technology. This is quite a difficult topic to deal with, particularly as a purely analytical approach presents us with some quite difficult mathematics. In fact, from the purely analytical perspective, there is a dearth of good technical material, such as published journal papers or electromagnetic texts, which devote any detailed content to the topic. Also, there are some quite subtle concepts in the related electromagnetic theory that require careful thought. To address the question, I want to firstly revisit some history on a related topic, which attracted a great deal of attention in the online world, particularly on YouTube. A number of YouTube videos were posted over the controversial claim by Dr. Walter Lewin that Kirchhoff's voltage law was for the birds, as it appeared to break down in the presence of time-varying, non-conservative electromagnetic fields. YouTube contributor Silicon Soup posted a couple of videos in support of Lewin's claim, and noted that other commentators, such as Electroboom and Mr. Bob DuHamel from Vocademy Electronics Technology, were mistaken in their assumptions about voltage gradients in conductors co-located with time-varying electromagnetic fields. Mr. DuHamel took issue with Silicon Soup's response, and in what follows in this video, I consider the controversy in some detail. In his video, YouTube contributor, Silicon Soup, demonstrates that negligible voltage is observed along a part section of a wire loop, threading the window of an energized multi-turn winding, formed on a highly permeable toroidal magnetic core. Silicon Soup is responding to the notion that there must be an induced EMF along a wire segment adjacent to a varying magnetic field, and which appears as a commensurate voltage gradient along the wire. As noted earlier, both Electroboom and Bob DuHamel claim that this voltage gradient must exist, and could be observed, in the case of a wire co-located with an energized solenoid winding. In Silicon Soup's experiment, the wire threading the toroid does not complete an encirclement of the toroid cross-section, so it's not a closed circuit carrying an induced electric current. To clarify this, I'll play the relevant sequence in Silicon Soup's video.
In my simple experiment, I wounded a single loop wire over a toroidal transformer coil and measured the voltages across the terminals and along the wire. The blue trace shows that there is some 130 mV across the terminals, but the red trace shows no voltage along half the loop. This proves that KVL fails and Faraday's law is needed for a proper explanation.
This result may be confusing to some people. Although the wire is not carrying current, there must be an observable voltage appearing across the wire endpoints or terminals. If an induced voltage is observed across the terminals of a closed wire loop threaded by the time-varying magnetic field, why isn't there a commensurate induced voltage observable along a partial loop segment, even if the loop is open and not carrying an induced current? In a YouTube video segment I'll show shortly, Mr. Bob DuHamel argues that the induced EMF must be present along the wire loop somewhere, and presents a demonstration in which he claims to observe a voltage along a wire segment, co-located with an energized solenoid. A time-varying magnetic flux phi is established in the highly permeable toroidal core material internal volume by the winding current I. I assume that the induced time-varying flux phi is confined entirely within the highly permeable toroidal core material volume, and that there is a negligible time-varying magnetic field external to the toroid core boundary. The closed loop path comprising wire segment B to A to C and the oscilloscope measurement path is threaded by the time-varying magnetic flux phi circulating in the toroidal core. This accounts for the non-zero voltage indication VBC for the relevant oscilloscope vertical input channel. There is an assumed zero or negligible time-varying magnetic field in the shaded region, enclosed by the single-loop wire segment A to C and the oscilloscope measurement path, which includes the alligator clips, the BNC cable and the oscilloscope channel vertical input circuitry. In the absence of any time-varying magnetic flux, linking the closed path formed by the wire segment A to C and the oscilloscope measurement path, there cannot be any resultant induced EMF around that closed path, as mandated by applying Faraday's law to that closed path. Therefore, VAC is 0 or negligible, as indicated for the relevant oscilloscope vertical input channel, monitoring the voltage between points A and C. If VAC is non-zero, it can only be accounted for by the presence of a time-varying magnetic flux linking the shaded area. I mentioned earlier a YouTube video in which Mr. Bob DuHamel conducts an experiment where he appears to measure a voltage gradient along a section of an open-loop conductor co-located with an energized solenoid. I'm showing in this video clip a short segment relevant to the discussion. The full video may be viewed on YouTube using the link, which will be in the video notes. Bob's intention in the video is to counter Silicon Soup's argument that there cannot be a voltage gradient along an open wire co-located with a time-varying magnetic field. Having seemingly demonstrated said voltage gradient, in the case of a solenoid, Bob reasons that, if a voltage gradient cannot be observed in the case of an energized toroidal inductor, there has to be a logical reason why not. So he reasons that the induced EMF must be entirely confined to the solenoid window. Is Bob correct about the seat of EMF in a toroidal inductor, based on his demonstration?
And they do measure a voltage gradient around here. And I measured it without having to be quite so careful, because I have a solenoid, literally a solenoid, because it's a solenoid that's a coil of wire that used to have an armature inside it. This is my coil of wire, and then I have a loop of wire to go around it. And if I have that loop go around, I'm going to get a current in this loop, or an attempted current at least, which is going to skew my reading over in my oscilloscope. But if I take that broken loop and make sure that my wire does not go around the solenoid. So there's my measuring wires, but then the loop is going to come back this way. As long as I don't go around the loop, I'm not going to induce any current in these wires, and it doesn't matter what their shape is. In fact, Robert Romer even mentions that in his paper, that if we have a solenoid and we have a loop around it, we're going to get X number of volts. If we have two loops, we're going to get 2 times that. But if we have another loop out here, we're going to get nothing, and it doesn't matter what these shapes are. I'm going to get the same voltage with that shape, or the same current, as I do with the circular shape. And this other shape, it can be whatever you want, but I'm not going to get any current there because it does not circle the solenoid. So as long as I don't circle that solenoid, I'm not affected by the magnetic field. So here I am measuring that voltage, and you can see I'm getting about 2 millivolts across this coil. And watch as I move the red lead. As I move it to the middle, I get a little less. As I move it down closer to the black lead, I get less and less. So there's clearly a voltage gradient along this part loop of wire. Of course, if I flip it around and have the loop go around the other side, then I'm not only going to be measuring the voltage on the loop, but also the voltage induced in the oscilloscope by the magnetic field, and I get a lot more voltage. But you can see that there is a clear voltage gradient along this loop of wire.
In his video, Bob refers to a 1982 paper by the American physicist Dr. Robert H. Romer, which was published in the American Journal of Physics. A graduate of Princeton University, Dr. Romer was a professor of physics at Amherst College, Massachusetts, where he had been a faculty member since 1955. In 1988, Dr. Romer was appointed as editor of the American Journal of Physics. The matter of the validity of Kirchhoff's voltage law in the presence of non-conservative fields is not discussed by Dr. Romer. In fact, the only laws he makes use of in the paper are Faraday's law and Ohm's law. Romer's paper is probably the most often quoted text in discussions concerning the validity of Kirchhoff's voltage law, which was raised in a controversial lecture presented by MIT professor Dr. Walter Lewin. Romer's figure 3 on the right is clearly the focus of Bob's attention when discussing the conditions under which Faraday induction does or does not arise. I want to make a clear distinction between what Robert Romer proposes about the nature of the time-varying magnetic field, and where this might be at odds with the state of the time-varying magnetic field in Bob DuHamel's experiment. Romer's underlying assumption, in the context of his paper, is that the time-varying magnetic field is confined within region 1, and there is zero time-varying flux in region 2. In his experimental study, confirming his theoretical predictions, Romer employs a long solenoid, which presumably satisfies this condition of the magnetic field confinement within region 1, as shown in the left-hand figure. What if the field is not confined within a well-defined, cross-sectional region, as shown in the right-hand figure? Consider the right-hand figure, and the annotations shown there. The dot convention shown in the central circular region would represent the time-varying flux intersecting the plane of the figure, being directed towards the observer at some time instant. At the same time instant, it is possible that all or part of the magnetic field return flux also intersects the plane of the figure, as indicated by the cross convention. That is, the return flux might be highly localized, rather than being remote from the region of interest, as would be the case for the energized long solenoid used by Robert Romer in his experiment. This situation is more likely for the case of the magnetic field produced by the energized solenoid used by Bob DuHamel in his experiment. If the field is not confined to region 1, as required in Romer's figure 3, the reasoning concerning the absence of Faraday induction, enclosed contours lying in region 2, breaks down. As shown in the right-hand figure, it would be possible for Faraday induction to occur in certain closed contours such as C2, which link time-varying magnetic flux. It might even be the case that for a contour, such as C4, there will be negligible resultant magnetic flux linked, and there would be negligible Faraday induction along that contour, as distinct from the case of contour C1, where induction would likely occur. As Bob DuHamel notes in his video, his version of a solenoid is the winding which produces the driving force in a current-driven electromechanical actuator. This image is representative of the typical solenoid actuator, found in common use in applications requiring a mechanical action, initiated by an electrical on-off control. Bob had removed the armature or mechanical plunger, leaving just the winding and exterior frame or yoke. Presumably, the exterior yoke would form part of the magnetic circuit which includes the winding and the moving armature. I suggest this form of a solenoid winding is not what Robert Romer had in mind when he designed the experiment outlined in his paper. In the preamble of his paper, Romer refers to his use of a long solenoid carrying a varying current. In section 5 of his paper, Romer describes his air-cored solenoid as being over a meter in length. He also notes that the magnetic field strength external to the winding boundary would be negligible, particularly where his observations were made, that is, in a plane orthogonal to the winding longitudinal axis, located midway between the solenoid endpoints. It's more likely that the winding I show here is more representative of the solenoid winding used by Bob DuHamel, with respect to the distribution of the magnetic field surrounding the energized winding. As noted, this was the low-voltage secondary winding extracted from a stripped-down mains transformer. With a squat coil shape like this, it's very likely the magnetic field distribution around the energized winding would more closely resemble the energized squat coil shown here, where the field is delineated using iron filings. The magnetic field flux lines would lie along highly localized closed paths. I now proceed to a video covering a set of experimental tests, in which I'm seeking to gain an understanding of the magnetic field conditions near an energized winding. What conditions exist which can lead to the flawed belief that a voltage gradient is physically possible in an open wire segment, co-located with a time-varying magnetic field? I start with the squat coil, mentioned in the previous slide. Having considered the field conditions around the squat coil, I then move on to the case of a long solenoid, typical of that used by Robert Romer in his experimental work. This is quite a long video segment, being just over 19 minutes in length. The viewer might choose to skip forward by that time difference, and avoid this part in the first instance. I envisage someone more interested in the theoretical study of the fields associated with a toroidal inductor might choose that option. If the viewer does make that choice, it may not be clear, as to why indeed there cannot be a voltage gradient in an open conductor segment. Shown here is the basic layout of the experiment, in which this coil is energized by applying a sinusoidal voltage to the winding terminals. A low-level 7.5 kHz sinusoidal signal is generated and amplified to drive the coil winding at several volts, producing an associated time-varying magnetic field. The coil winding AC drive comes from this audio power amplifier. The 12-volt DC power for the amplifier may be turned on and off via a toggle switch. To reduce possible mains interference with the measurements, no AC mains power devices or sources are used anywhere in the setup. The small signal input for the audio power amplifier is connected as shown here. To ensure there is a clean 7.5 kHz sine wave applied to the audio amplifier input, the input signal is pre-filtered through this electronics board. This direct digital simulator unit is the primary source of the 7.5 kHz signal. To obtain an exact 7,500 Hz, whilst taking observations, I found I needed to add a small offset of 3 Hz. This metal box doubles as a shielded enclosure for 2 different small signal processing functions. On the right-hand side is an AC to DC converter, and on the left-hand side, a basic narrow-band AC amplifier. The AC to DC converter takes a small signal AC input at 7.5 kHz to produce an output DC value equivalent to approximately 36 times the RMS value of the input signal. The narrowband small signal amplifier accepts a 7.5 kHz sinusoidal input which is amplified by a factor of approximately 36 times. In the case shown here, the AC to DC converter output is being monitored on this digital multimeter set on DC range. The indicated voltage is thus the amplified DC equivalent of the RMS value of the 7.5 kHz signal currently being applied to the AC to DC converter input port. Except for a small gap at the terminals, this copper strap loop almost encloses the time-varying magnetic field produced by the current in the energized coil. The test leads connected to the open terminals of the loop convey the induced loop EMF to the AC to DC converter input. The multimeter indication is the DC equivalent of the induced EMF RMS value amplified 36 times. With the primary coil energized, there will be an EMF induced in the copper strap loop encircling the coil. The EMF will appear as an AC potential difference across the gap. The voltmeter, on DC range, is monitoring the DC equivalent of the induced loop EMF applied to the AC to DC converter circuitry. Here I'm observing the primary coil input driving parameters, both voltage and frequency. This smaller multimeter is monitoring the AC to DC converter output, related to the copper loop induced EMF. The other multimeter here is connected in parallel with the wire pair from the audio power amplifier output. The coil AC drive voltage is indicated on the multimeter voltage function. When switched to monitor the driving frequency, I have confirmation of the 7.5 kHz source frequency derived from the DDS generator. I use this small search coil to understand how the time-varying magnetic field spreads out around the energized primary coil. Any time-varying flux linked by the search coil will produce an EMF in the search coil, which can be monitored. With the search coil placed directly on top of the energized winding, I would expect to see the maximum induced EMF, given the close proximity of the winding and the search coil. Again, I'm using the AC to DC converter to monitor the induced EMF. If I switch off the primary coil drive, then as expected, there is no induced EMF in the search coil. With the search coil off to one side of the primary coil, the induced EMF is clearly lower as might be expected. It is clear that there is still flux linking the search coil some distance away from the primary coil. It is certainly clear that the primary magnetic field spreads out some distance from the energized coil. So, the magnetic field for this coil is not highly localized, as might be expected with the magnetic field produced within a classical long solenoid winding, for example. This observation is relevant to what follows. Here I am duplicating the experiment mentioned in Bob DuHamel's video, in which he claims to observe a voltage gradient along a part segment of an open loop adjacent to the time-varying magnetic field in his solenoid. In this situation, I'm looking for any induced voltage along roughly half the total loop length. I obtain this DC value of around 125 millivolts, which is the AC to DC conversion, multiplied by about 36 times. On moving the monitoring point to encompass about 1/4 of the loop length, the observed equivalent RMS voltage has fallen to around 80 millivolts DC. With the very small loop segment seen here, the DC output is about 20 millivolts. Does this confirm that there is an actual voltage gradient along the open loop segment? There are a couple of points to note here. Firstly, I know the total equivalent loop EMF was observed earlier to be of the order of 600 millivolts. In the first half loop length segment test, I observed only 125 millivolts. This value is inconsistent with what would be an anticipated induced voltage of approximately 300 millivolts along the half-loop segment. Secondly, I know from the search coil observations that the time-varying magnetic field spreads out around the energized winding. Therefore, what could be mistaken as a voltage gradient along the copper loop segment is simply the Faraday-induced EMF arising from the time-varying flux linking the measurement loop. Clearly, as the measurement loop decreases in size, and confirmed by the observations, one would expect a lower induced EMF in the measurement loop with less flux linking the loop. It is often stated in the literature that an energized long, tightly pitched, solenoid winding produces almost negligible magnetic field exterior to the winding boundary, particularly at the longitudinal midpoint. This is a long solenoid I have used for a number of experiments, and which appears to meet the aforementioned characteristic. It is 93 centimeters long, with some 300 turns of insulated wire on a 6 centimeter diameter former. It has a self-inductance of approximately 330 microhenry. I'm going to focus initially on this copper strap wrapped around the winding midpoint and which forms an almost complete encirclement of the solenoid. The strap endpoints can just be seen here when viewing underneath the winding. Here the solenoid is energized with the same 7.5 kHz sinusoidal drive sourced from the audio power amplifier. Measurement leads may be seen connected to the copper strap endpoints. Once again, the measured signal is input to the AC to DC conversion circuit. The DC output to the multimeter on the left is the RMS equivalent of the induced EMF in the copper strap, which is effectively a single-turn secondary coupled with the solenoid primary winding. The multimeter on the right is monitoring the solenoid AC excitation, which is around 6 volts RMS at 7.5 kHz. As a check, I note when the 12-volt DC supply to the audio amplifier is switched off, the solenoid excitation is interrupted, as suggested by the change in the meter indications. Another single-turn secondary can be seen enclosing the solenoid winding at its midpoint, and which is terminated in a 150K resistor at the terminal block. With the solenoid energized, the induced loop EMF is monitored by the multimeter, which may be seen is set on AC range. The reading of about 530 mV should be taken with some caution, as the multimeter AC range frequency response may be inadequate at 7.5 kHz in providing an accurate voltage indication. Notwithstanding this caveat, the aim here was to show that the secondary induced EMF parameters were consistent with the solenoid primary winding AC excitation conditions. This appears to be confirmed by the indicated 7.5 kHz indication when the multimeter is switched to the frequency range. I note that, as can be seen in this test setup, the secondary loop terminals are monitored via the AC narrowband amplifier stage in the signal processing box rather than the AC to DC converter used up to this point in the experiment. As demonstrated earlier, when the solenoid primary winding AC energization is turned off, the secondary induced EMF is interrupted, as may be seen by the change in the multimeter indications. I now return to the copper strap, single-turn secondary at the solenoid midpoint. Soldered to the strap are a number of tapping points, where test leads may be connected. These points are of use in determining if there is any voltage gradient along part of the open secondary. With the solenoid energized, I start by monitoring a segment of the open secondary loop, from about the loop midpoint to the endpoint or terminal closest to the viewer. With the probed signal connected to the AC to DC conversion function, the indicated 5 mV DC is in the order of 80 to 100 times less than the EMF of 400 mV previously observed when monitoring the closed-loop induced EMF. The right-hand side multimeter switched to AC range indicates the same solenoid excitation parameters observed earlier. As I move the red test lead closer to the loop endpoint, there is a 3 to 4 mV change in the DC reading. Clearly, there is no compelling argument here for the presence of a significant voltage gradient along the open loop conductor, which is in any way commensurate with the induced loop EMF observed earlier. With both test leads now connected to the same loop terminal, there is no observable change in the right-hand multimeter DC voltage indication. If there was a voltage gradient between the previous tapping point and the end terminal, then it is undetectable. To reiterate, with the primary solenoid winding energized, there is clearly no experimental confirmation of any commensurate voltage gradient along the partial segment of the open loop copper band. Earlier in this video, I used a search coil to gain an understanding of how the magnetic field spread out around the squat coil used in the early part of this demonstration video record. I introduce another method for surveying the magnetic field distribution and applying it to the fields both external to the long solenoid winding and within the solenoid interior. In this case, the sensor used is a very small ferrite cord RF choke, shown here by way of example. It so happens this component works very well as a time-varying magnetic field sensor. Given the small size of the RF choke, it's possible to monitor the field at quite specific locations, in the space near and around the solenoid winding. There are 3 situations in which I use these RF chokes as field sensors. 2 are placed at fixed locations and a third can be moved around freely. This is the movable field probe. Essentially, it's a ballpoint pen with the internal pen part removed, with an RF choke fitted at the tip, as shown. Connecting wires, soldered to the choke leads, convey the time-varying induced EMF to the measurement point. This fixed field probe works on the same principle as the movable probe, but is intended for insertion into the interior of the solenoid winding to monitor the field inside the solenoid. There is another probe, mounted close to the top of the winding, and this will be seen as the video proceeds. Here I'm inserting the fixed probe into the solenoid interior. The magnetic field distribution associated with the time-varying current in the solenoid winding is examined here in detail. The induced EMF, produced in the probe inserted into the solenoid interior, is considered first. The signal from the probe is input to the narrow-band AC amplifier in the signal conditioning box, where it is amplified by a factor of approximately 36 times. Accordingly, the multimeter is connected to the AC amplifier output and set on the AC range for voltage measurement. I reiterate that at the operating frequency of 7.5 kHz, the multimeter voltage indication may not truly reflect the actual RMS value of the amplified probe-induced EMF. Suffice to say, there is a significant induced EMF in the internal probe at its location within the solenoid. Switching the multimeter to the frequency range verifies that the induced EMF frequency is consistent with the 7.5 kHz driving voltage sourced from the audio power amplifier output. Switching off the 12-volt DC supply to the audio power amplifier confirms that the internal probe-induced EMF is interrupted due to the loss of solenoid winding current and the associated time-varying magnetic field. The next observation is of the induced EMF in the aforementioned fixed surface field probe, seen placed here, on the top of the solenoid winding. This is one key element in confirming theoretical expectations of the magnetic field behavior associated with the long solenoid energized winding. The orientation of the RF choke sensor is such that lines of magnetic flux running parallel to the winding longitudinal axis would tend to correlate with a higher value of induced EMF. This would be suggested by consideration of the direction of the magneto-motive force surrounding a wire carrying an electric current. As before, the signal from the probe is input to the narrow-band AC amplifier in the signal conditioning box, where it is amplified by a factor of approximately 36 times. Notwithstanding the close proximity of the sensor to the winding current, there appears to be almost negligible induced EMF in the sensor, registering on the multimeter. The final set of observations are those made with the movable field probe discussed earlier. The first two observations are with the probe aligned along the surface of the solenoid winding, firstly near the copper strap secondary loop. As with the case of the fixed surface probe, there is negligible induced EMF in the sensor. The observed EMF value is vastly different to that observed with the internal field probe. Here I check that there is agreement with the negligible value of the induced EMF observed with the fixed probe and with this movable probe. Lest there be any doubt that this probe is actually responding to the solenoid fields, I show that there is a clear response when the probe is inserted at the opposite end of the winding. This again confirms that there is substantial difference between the internal and external magnetic field strengths associated with the solenoid winding current. Rather than identifying the location of the seat of EMF in the primary winding of a toroidal inductor, I'm considering where the EMF might arise along a secondary path, which threads the toroidal window. I propose for analysis the Amperian path or secondary loop, shown in red in the diagram. Depending on which segment of the overall path I'm considering, choosing this arrangement allows me to focus solely on either Z-directed or X-directed vector field components in that segment. As will be shown, the problem can be reduced to analyzing the intersection of the Amperian loop, which is coplanar with the 2D XZ plane, and the time-varying magnetic flux phi in the toroidal core. Shown here on the right is the cross-section of the toroidal core flux as viewed on the XZ plane. The core flux for a static current I amperes may be found from the relationships shown on the left. The primary winding, magnetic core parameters and driving current fully determine the core magnetic flux. In SI units, the flux is typically stated in Webers. For the case of a time-varying primary current at a relatively low frequency, one may assume that the static current term I may be replaced by the time-varying current relationship without a significant loss of generality. This assumption comes under the general heading of the so-called quasi-static approximation, a terminology regularly found in electromagnetic texts. It is well established in the electromagnetic theory literature that the on-axis magneto-motive force, or MMF, for a filamentary current loop is governed by the relationships shown here. It is left to the viewer to independently check the development of the relationships from other sources. I show this slide as a precursor to the next slide, where I present the closely related dual relationship which exists for the magnetic vector potential for a filamentary ring of magnetic flux. As noted in the previous slide, there is a dual relationship between the MMF field of a current ring and the vector potential of a flux ring. Shown here is the development of the relationship for the on-axis magnetic vector potential of a filamentary flux ring. Again, it is left to the viewer to work through the derivation method shown here. This analysis applies only to the on-axis case, which may be used as a basis for the derivation for the more general case of the off-axis vector potential at any location in the 3D space occupied by the flux ring. This is a necessary stage in supporting the analysis that will be introduced later. While the relationship shown applies particularly to a flux filament, one can justifiably extend the concept to a larger cross-sectional area of flux, by reasoning that the larger flux cross-section may be treated as a manifold accumulation of flux filaments. I note here that the equations shown in this slide apply to the magnetostatic case. As suggested earlier, it is possible to extend the analysis to the quasi-static case, where the ring flux varies with time. Here, I show the development of the on-axis vector potential for a time-varying flux, and the transformation of the relationship for the vector potential to the equivalent on-axis electric field strength. One simply takes the negative of the derivative of the vector potential to obtain the electric field strength. I raise this point, as mandated by Maxwell's equations, there is a direct relationship between the induced electric field and Faraday-induced EMF. What should be quite clear is that the on-axis electric field associated with a time-varying ring of magnetic flux is continuous in the space beyond the plane of the flux ring. Extending the filamentary flux ring model to the total flux in a toroidal core should lead to the same conclusion, that the on-axis induced electric field is not limited to the toroidal core window. In determining the value of the magnetic vector potential at some arbitrary point P in the 3D space around the flux ring, we must undertake a more complex analysis. The vector potential components at off-axis point P on the XZ plane may be stated in terms of cylindrical coordinates. One firstly determines the relationships for the infinitesimal vector potential components at point P that arise from an infinitesimal flux segment of length dl at some point Q on the flux loop. Point Q is located by its cylindrical coordinates, as shown on the diagram. Point P is located at line-of-sight distance S from Q. Consider also another point Q primed, which also lies on the flux loop, and which is at the same line-of-sight distance S from point P. I then consider the vector potential contribution at point P from an identical infinitesimal flux segment of length dl at Q primed. By symmetry, it should be clear that the vector contribution from x-directed flux components arising from points Q and Q primed will cancel one another, and that only the y-directed flux components in the loop will determine the overall vector potential at P. The resulting geometric orientation arising from the off-axis position of point P in relation to points Q and Q primed means the spatial disposition of the resulting vector potential varies when one mathematically integrates the contribution from all infinitesimal flux elements in the loop. The complexity in the analysis arises in resolving those components of the overall vector contribution from the flux loop at P, which align with the ρ and z directions, as they would exist exclusively on the xz plane. The result of this process will be presented in the next slide. The diagram on the right shows the intersection of the xz plane and an energized toroidal core lying centered in the xy plane. Rather than attempting to cover the analytical process in detail, I will simply state the results for the vector potential components in the ρ and z directions. The results are based on the model of the filamentary flux loop, as shown in the previous slide. Clearly, the flux confined to the energized toroidal core is not a flux filament. Nevertheless, the results obtained for the filamentary model can be reasonably extended as an approximation for the toroidal model, where the flux path has a finite cross-section. The vector potential components in the ρ and z directions at some point P on the xz plane are determined by the relationships on the left. As noted, E1 and E2 are, respectively, first and second kind complete elliptic integrals, which can be determined from the indicated equations. The indicated integrals have no closed solutions and are typically solved by numerical methods. Approximations for elliptic integrals can be found in various texts and online sites. For example, the text by H.B. Dwight contains a section stating solutions for elliptic integrals. For completeness, I repeat the relationships for the flux value in the toroidal core, which are based on the core physical dimensions, the core material magnetic properties, and the winding current. There are other sources which discuss the topic of fields of a torus, such as this 1995 paper by Neal Carron, published in the American Journal of Physics. While not essential reading, I would recommend this paper, as it covers the topic in great detail, including a comprehensive analysis in the appendix. Carron's analysis takes a different approach to that used in this video, but provided some care is taken in applying the relevant equations, the results are consistent. The topic is also covered in Wikipedia, under the heading of Magnetic Vector Potential, where there is a specific section covering the depiction of the vector potential in the region surrounding an energized toroidal winding. As proposed earlier in the video, I suggest looking at the distribution of the induced EMF around a rectangular Amperian loop, as shown in the diagram. The values chosen for the loop dimensions and the toroidal winding parameters are quite arbitrary, but with some notion of what those values might be in a practical situation. Once the vector potential distribution is resolved, it is a relatively simple process to then find the induced electric field strength at any point around the rectangular path. I recall that the electric field strength is obtained as the time derivative of the vector potential. The equations for the vector potential were solved for the specific physical values shown. I used the open-source software Scilab to obtain the solutions, using numerical methods to solve for the elliptical integral components. As noted, the induced electric field components along the individual segments will be determined by the rate of change of the varying vector potential along each segment. The induced electric fields will be directed opposite to the vector potentials and are determined from the various relationships shown here. Having deduced the induced electric field strengths along the segments, it then remains to integrate the induced electric field terms over each loop segment length. The integral terms then yield the individual induced EMF contributions from each of the four segments. Finally, the sum of the individual EMF contributions from each segment will yield the induced Faraday EMF along the entire closed Amperian loop path. For completeness, I provide various graphs, which may assist in visualizing the distribution of the fields in the various segments of the loop. Shown here are plots of the vector potential, electric field strength and EMF contribution along the Amperian loop segment between points P and Q. I note a key point, that based on the induced field direction, the progressive EMF in the segment increases in magnitude from point Q towards point P. Shown here are plots of the vector potential, electric field strength and EMF contribution along the Amperian loop segment between points G and F. The progressive EMF increases in magnitude in the traversal from point G towards point F. Shown here are plots of the vector potential for the right-hand and left-hand Amperian loop segments, P to G and F to Q. Shown here are plots of the electric field strengths and EMF contributions along the Amperian loop right-hand and left-hand segments. The progressive EMF magnitude increases from point P towards point G on the right-hand segment and from point F towards point Q on the left-hand segment. I'm showing here a closer view of the toroidal core window. Points A and B mark the upper and lower boundary lines of the core window height. I calculate the EMF contribution along the right-hand side segment, which sits within the core window between the points A and B. The EMF contribution increases from point A towards point B. The EMF contribution within the core window is 126 mV, which is approximately 37% of the total closed loop EMF of 339 mV around the closed Amperian loop. The analysis clearly shows that while a significant proportion of the loop EMF is induced within the core window, the greater proportion is induced in the remainder of the closed path, which is threaded by the toroidal core time-varying flux. Suppose now that the purely non-material Amperian loop, PQFG, is replaced with a resistive wire loop, formed from uniform resistivity material, having the same cross-sectional area along each segment. Provided conditions are quasi-static, the closed resistive path, driven by the underlying loop EMF, would mandate that a uniform current would be established along the closed loop path. From Ohm's law, we would expect the following ohmic voltage drops for each segment. The established induced EMF contributions along each segment are repeated here. How do we account for the discrepancy between the induced EMF contributions along each loop segment, if the actual ohmic voltage drops are quite different in each case? We can only account for the discrepancy by proposing the existence of Coulomb electric fields along the loop segments, which would be established by surface charge density gradients, appearing virtually instantaneously around the closed loop path resistive conductor segments. The Coulomb charge-based electric fields would arise naturally, to ensure the loop current is everywhere the same around the closed loop. The conservative potential differences that would exist along a loop segment would be related to the difference between the ohmic voltage drop and the induced EMF for that segment. As would be expected for the case of charge-based conservative potential differences, the sum of those potential differences would be zero. This expectation is consistent, as prior to the energization of the primary winding, the secondary loop PQFG would be overall electrically neutral. That electrical neutrality must be preserved, even with the primary winding energized and steady-state current flowing in the loop. Given the electrical neutrality is preserved, there could not be any net Coulomb potential difference accrued in a full traversal of the closed loop path. What would be revealed by taking a measurement of the voltage between points F and Q, for example? The indicated voltage would correspond to the ohmic voltage change, UFQ. The underlying EMF component along segment FQ is masked by the Coulomb potential difference, VFQ. There is no direct means by which we would be able to measure the EMF component along segment FQ. The underlying loop EMF will always appear as the summation of the various ohmic voltage changes encountered in a traversal of the closed loop path.